treating smart pointers like regular references with the Deref trait. Implementing the Deref trait allows you to customize the behavior of the dereference operator as opposed to the multiplication or glob operator. By implementing deref in such a way that a smart pointer can be treated like a regular reference, you can write code that operates on references and use that code with smart pointers too. Let's first look at how the dereference operator works with regular references. Then we'll try to define a custom type that behaves like box T and see why the dereference operator doesn't work like a reference on our newly defined type. We'll explore how implementing the deref trait makes it possible for smart pointers to work in a similar way as references. Then we'll look at Rust's deref coercion feature and how it lets us work with either references or smart pointers. Note, there's one big difference between the myBoxT type we're about to build and the real box T. Our version will not store its data on the heap. We're focusing this example on deref, so where the data is actually stored is less important than the pointer-like behavior. Following the pointer to the value with the dereference operator. A regular reference is a type of pointer, and one way to think of a pointer is an arrow to a value stored somewhere else. In listing 15.6, we create a reference to an I32 value and then use the dereference operator to follow the reference to the data. At the bottom, assert equals 5 dereference y. The variable x holds an I32 value, 5. We set y equal to a reference to x. We can assert that x is equal to 5. But if we want to make an assertion about the value in y, we have to use dereference y to follow the reference to the value it's pointing to, hence dereference. Once we dereference y, we have access to the integer value y is pointing to that we can compare with 5. If we tried to write assert equals 5 and y instead, we would get this compilation error. Error 277, can't compare an integer with a reference to integer. The trait standard compare partial equals reference to integer is not implemented for integer. Comparing a number and a reference to a number isn't allowed because they're different types. We must use the dereference operator to follow the reference to the value it's pointing to. Using box like a reference. We can rewrite the code in listing 15.6 to use a box instead of a reference. The dereference operator will work as shown in listing 15.7. The only difference between listing 15.7 and 15.6 is that here we set y to be an instance of a box pointing to the value in x, rather than a reference pointing to the value of x. In the last assertion, we can use the dereference operator to follow the box's pointer in the same way that we did when y was a reference. Next, we'll explore what is special about box that enables us to use the dereference operator by defining our own box type. Defining our own smart pointer. Let's build a smart pointer similar to the box type provided by the standard library to experience how smart pointers behave differently from references by default. Then we'll look at how to add the ability to use the dereference operator. The box T type is ultimately defined as a tuple struct with one element, so listing 15.8 defines a myBox type in the same way. We'll also define a new function to match the new function defined on box. Struct myBox. Type T takes T implement T myBox T function new x t returns my box t, my box x. We've defined a struct named myBox and declare a generic parameter t because we want our type to hold values of any type. The myBox type is a tuple struct with one element of type t. The myBoxNew function takes one parameter of type t and returns a myBox instance that holds the value passed in. Let's try adding the main function in listing 15.7 to listing 15.8 and changing it to use the myBox type we've defined instead of box. The code in listing 15.9 will not compile because Rust doesn't know how to dereference myBox. Here's the resulting compilation error. 614, type myBox integer cannot be dereferenced. Our myBox type can't be dereferenced because we haven't implemented that ability on our type. To enable dereferencing with the Dereference operator, we implement the Deref trait. Treating a type like a reference by implementing the Deref trait. As discussed in Chapter 10, to implement a trait, we need to provide implementations for the trait's required methods. The Deref trait, provided by the standard library, requires us to implement one method named Deref that borrows self and returns a reference to the inner data. Listing 15.10 contains an implementation of Deref to add to the definition of myBox. Use standard ops Deref, implement t Deref for myBox t. Type target equals t. Function Deref takes a reference to self, returns reference to t, and the body is reference to self.0. The type target equals t syntax defines an associated type for the Deref trait to use. Associated types are a slightly different way of declaring a generic parameter, but you don't need to worry about them for now. We'll cover them in more detail in Chapter 19. We fill in the body of the Deref method with reference to self.0, so Deref returns a reference to the value we want to access with the Deref operator. The main function in listing 15.9 that calls Deref on the myBox value now compiles and the assertions pass. Without the Deref trait, the compiler can only dereference references with ampersands. The Deref method gives the compiler the ability to take a value of any type that implements Deref and call the Deref method to get an ampersand reference that it knows how to dereference. When we entered asterisk y in listing 15.9, behind the scenes, Rust actually ran this code. Asterisk and then y.deref. Rust substitutes the asterisk operator with a call to the Deref method and then a plain dereference, so we don't have to think about whether or not we need to call the Deref method. This Rust feature lets us write code that functions identically whether we have a regular reference or a type that implements Deref. The reason the Deref method returns a reference to a value, and the reason that the plain dereference outside the parentheses in star parentheses y.deref is still necessary is the ownership system. If the Deref method returned the value directly instead of a reference to the value would be moved out of self. We don't want to take ownership of the inner value inside myBox in this case or in most cases where we use the Dereference operator. Note that the Dereference operator is replaced with a call to the Deref method and then a call to the Deref operator just once each time we use a Deref operator in our code. Because the substitution of the asterisk Deref operator does not recurse infinitely, we end up with data of type i32 which matches the 5 in assert equals in listing 15.9. Implicit deref coercions with functions and methods. Deref coercion is a convenience that Rust performs on arguments to functions and methods. Deref coercion converts a reference to a type that implements deref into a reference to a type that deref can convert the original type into. Deref coercion happens automatically when we pass a reference to a particular type's value as an argument to a function or method that doesn't match the parameter type in the function or method definition. A sequence of calls to the deref method converts the type we provided into the type the parameter needs. Deref coercion was added to Rust so that programmers writing function and method calls don't need to add as many explicit references and dereferences with ampersands and asterisks. The deref coercion feature also lets us write more code that can work for either references or smart pointers. To see deref coercion in action, let's use the mybox type we defined in listing 15.8, as well as the implementation of deref that we added in 15.10. 15.11 shows the definition of a function that has a string slice parameter. Function hello takes name of type reference to string, and then print line hello name. We can call the hello function with a string slice as an argument, such as hello static slice Rust, for example. Deref coercion makes it possible to call hello with a reference to a value of type mybox, as shown in listing 15.12. Here we're calling the hello function with the argument $m, which is a reference to a mybox string value. Because we implemented the deref trait on mybox in listing 15.10, Rust can turn $mybox string into $string by calling deref. The standard library provides an implementation of deref on string that returns a string slice, and this is in the API documentation for deref. Rust calls deref again to turn the $string into $stir, which matches the hello function's definition. If Rust didn't implement deref coercion, we would have to write the code in listing 15.13 instead of the code in 15.12 to call hello with a value of type $mybox string. The *m dereferences the mybox string into a string. Then the ampersand and the range, I guess, take a string slice of the string that is equal to the whole string to match the signature of hello. The code without deref coercions is harder to read, write, and understand with all these symbols involved. Deref coercion allows Rust to handle these conversions for us automatically. When the deref trait is defined for the types involved, Rust will analyze the types and use deref as many times as necessary to get a reference to match the parameter's type. The number of times that deref needs to be inserted is resolved at compile time, so there's no runtime penalty for taking advantage of deref coercion. How deref coercion interacts with mutability. Similar to how you use the deref trait to override the asterisk operator on immutable references, you can use the deref mute trait to override the asterisk operator on mutable references. I think I said immutable the first time. Deref overrides the asterisk operator on immutable references, and you can use deref mute to override the asterisk operator on mutable references. Rust does deref coercion when it finds types and trait implementations in 3 cases. From $t to $u when t is of type deref target equals u. From $mute t to $mute u when t is of type deref mute target equals u. And from mutable reference to t to reference to u when t is of type deref target equals u. The first 2 cases are the same except for mutability. The first case states that if you have a reference to t and the t implements deref to some type u, you can get a reference to u transparently. The second case states that the same deref coercion happens for mutable references. The third case is trickier. Rust will also coerce a mutable reference to an immutable one, but the reverse is not possible. Immutable references will never coerce to mutable references. Because of the borrowing rules, if you have a mutable reference, that mutable reference must be the only reference to that data, otherwise the program wouldn't have compiled. Converting one mutable reference to one immutable reference will never break the borrowing rules. Converting an immutable reference to a mutable reference would require that there is only one immutable reference to that data, and the borrowing rules don't guarantee that. So Rust can't make the assumption that converting an immutable reference to a mutable reference is possible.